Hi, I'm Rajiv from group B16, and I'm going to talk about proof by contraposition. Alright, first before talking about the contrapositive of a statement, we'll talk about the implication. So an implication is the statement that if P is true, then Q is true. And that statement is defined, technically, by its truth table values. And if we look at the truth table values, if P is true, then Q is true. Yeah, you can see that that's satisfied. If P is true, then Q is true. Oh, but true is false, so this statement has to be false. And then the implication says nothing about Q if P is false, so those can always be true. Alright. Now, an implication is equivalent, so saying P then Q is equivalent to saying that if the negation of Q is true, then the negation of P is true. Two statements are equivalent if they have the same truth table values, so it's pretty easy to see that they're equivalent if we just go through and fill in the truth table. So P is true and Q is true, that satisfies the implication. The negation of Q is false and negation of P is false, that also satisfies it. And the only time these could really be false is when the first value is true and the other value is false. So both of these have that. So both of these are false. Alright, and then if you look at the other values, then they all satisfy the implication, so true. Now, if you look at the truth table values, they're all the same. True and true, false and false, true and true, true and true. So that pretty much proves exhaustively that the contrapositive of a statement is the equivalent of the initial implication. Now, just looking at some real-world examples that are easily relatable, we have the statement that if something is a square, then it's a rectangle. And it follows from that, if something's not a rectangle, then it's not a square. Alternatively, you could say, if it's raining, then it's cloudy. Then that implies that, if that statement is true, then if there are no clouds, then it's not raining. Alright, so proof by contraposition uses the fact that a contrapositive is the equivalent statement of the initial implication. So usually with a direct proof, you start by assuming P is true, and then you'd have to prove that Q is true. So as long as you prove that P is true and if Q is true whenever P is true, then you're proving that this implication is always true. Now, sometimes it's difficult to do a direct proof, and it's easier to use the contrapositive of a statement that if not Q, then P. Then not P, I mean. And so you start out by assuming not Q is true, and then you have to prove that not P is true. And so when you prove that, then you're proving the initial statement. The first example I'm going to do is proving that if x is irrational, then negative x is irrational. This is a little bit difficult to prove directly because writing out a general form for an irrational number is a lot more difficult than writing out the general form of a rational number. So instead of proving if x is irrational, then negative x is irrational, we'll then prove the statement that if the negation of negative x is irrational, then the negation of x is irrational is true. Forgot an L there. Alright, so because a real number, can only be rational or irrational, saying that the negation of negative x is irrational is the same as saying that negative x is rational. And so we'll change that to if negative x is rational, then x is rational. Alright, so we can start out by writing that negative x is equal to b over a, where b is some integer and a is some integer, and that's just the definition of a rational number. So then we can multiply both sides by -1 and say that x is equal to -1 times b divided by a. Now, we're not going to prove it right now, but we'll use the fact that the product of two integers is an integer. So -1 times b over a is some integer, and we're going to call that integer k. So x equals k over a. And because x can be written as the quotient of two integers, x is then rational. So we've just proven the second half of the statement follows when the first half is true. So because we've proven that statement, we have proven our initial statement, that if x is irrational, then negative x is irrational. Now the second example we're going to do is proving that if n cubed plus 5 is odd, then n is even. Now the reason this is easier to do by contraposition is that this is easier to write out in a general form than this. So how we're going to prove this is that if the negation of n is even is true, then the negation of n cubed plus 5 is odd is true. And because an integer, where n is an integer, I forgot to mention that, and because an integer can be only odd or even, we have the statement, we can then change this to the statement that if n is odd, then n cubed plus 5 is even. Alright, so we'll start out by writing out n is equal to 2k plus 1. That's just the general form of an odd number where k is some integer. Alright, now n cubed plus 5 would then be equal to 2k plus 1 cubed plus 5. Alright, and so let's just expand this out really quickly. We'll get 2k plus 1 times 4k squared plus 4k plus 1, and then we can't forget the 5 on the end right there. Alright, and let's see, if we look at this, we get 8k cubed, and looks like 12k squared, and let's see, 4 and 2, that looks like 6k, and 1. And then, again, can't forget the 5, all-important 5 on the end. Alright, and so we can write this then as 8k cubed plus 12k squared plus 6k plus 6, because we're just adding on the 5 right here. And then we can factor out a 2. 2 times 4k cubed plus 6k squared plus 3k plus 3. Alright, and because this right here is some integer, let's just call it a, n cubed plus 5 is equal to 2 times a. And that's just the general form of an even number. So we have just shown that if n is odd, then n cubed plus 5 has to be even. So because we've proven the contrapositive of the initial statement, because they're equivalent, we've just proven the initial statement that if n cubed plus 5 is odd, then n is even. So I hope that helped clarify how to use proof by contraposition. Thanks for watching.